What specific problem does the CAT4D method aim to solve in the context of 4D reconstruction, and how does it differ from existing approaches?
The CAT4D method aims to solve the problem of 4D reconstruction from monocular video inputs, specifically, addressing the challenges posed by the lack of synchronized multi-view video data for dynamic scenes. Unlike existing approaches that often require multiple synchronized videos or additional supervisory signals, like depth maps or segmentation masks, CAT4D utilizes a multi-view video diffusion model to transform a single monocular video into consistent multi-view videos. This allows the model to generate images at novel viewpoints and times without relying on extensive external data. Furthermore, CAT4D optimizes a deformable 3D Gaussian representation directly from the generated multi-view videos, which contrasts with prior methods that depend on complex multi-prior systems. Overall, CAT4D's approach significantly enhances the quality of 4D reconstruction while minimizing the need for additional data and supervision.
How does the proposed CAT4D method work? Illustrate the process step by step, including the roles of the multi-view video diffusion model and the deformable 3D Gaussian representation.
The proposed CAT4D method operates in a two-stage process to create a dynamic 3D scene from a monocular input video. First, it employs a multi-view video diffusion model to transform the input monocular video into a multi-view video, generating images at specified viewpoints and times based on the input frames. This model is trained on a curated dataset that includes real and synthetic data, allowing it to learn the joint distribution of target images conditioned on camera parameters and timestamps. In the second stage, the generated multi-view videos are used to reconstruct a dynamic 3D scene by optimizing a deformable 3D Gaussian representation, which is achieved through a photometric reconstruction loss. This approach enables the model to produce consistent multi-view videos that facilitate accurate 4D reconstruction, effectively decoupling camera motion from scene dynamics.
Can you provide a simple yet illustrative example demonstrating the inner workings of CAT4D, including how it generates multi-view videos from a monocular input?
CAT4D operates through a two-stage process to generate multi-view videos from a monocular input video. First, it utilizes a multi-view video diffusion model that takes a set of input images, along with their corresponding camera parameters and timestamps, to generate target frames at specified viewpoints and times. For instance, given a monocular video with a few frames, CAT4D selects camera viewpoints through farthest point sampling and generates a grid of images by conditioning on these selected frames. The model alternates between multi-view sampling, which ensures consistency across different viewpoints, and temporal sampling, which maintains consistency over time. This alternating strategy allows CAT4D to produce a coherent multi-view video that can then be used for dynamic 3D scene reconstruction.
What are the theoretical or practical benefits of using CAT4D over previous methods, particularly in terms of reconstruction quality and reliance on additional supervision signals?
The CAT4D model offers significant theoretical and practical benefits over previous methods, particularly in reconstruction quality and reduced reliance on additional supervision signals. Unlike existing models that require multiple synchronized videos and additional supervisory signals such as depth maps or segmentation masks, CAT4D utilizes a multi-view video diffusion model to transform a monocular video into multi-view videos without needing these extra inputs. This allows CAT4D to achieve comparable reconstruction quality to state-of-the-art methods like shape of motion and MOSCA, which depend heavily on external information. Furthermore, CAT4D demonstrates improved performance in dynamic scene reconstruction, particularly in scenarios where prior methods struggle with inconsistencies due to dynamic motion. Overall, CAT4D's approach enhances the robustness and accessibility of 4D reconstruction, making it more practical for users without specialized equipment or extensive datasets.
How is CAT4D validated or tested? Describe the experimental design, datasets used, and metrics for performance assessment.
CAT4D is validated through a series of experiments that assess its performance on various tasks, specifically focusing on its ability to generate images at novel viewpoints and times, perform sparse view static 3D reconstruction, and execute 4D reconstruction from monocular videos. The experimental design involves using the NSFF dataset, which contains synchronized camera data for dynamic scenes, and the DieCheck dataset, which includes challenging real-world video sequences. For performance assessment, qualitative and quantitative comparisons are made against existing methods such as 4DIM, CAT3D, shape of motion, and MOSCA, with metrics including reconstruction quality and the ability to control camera and scene dynamics separately. The results demonstrate that CAT4D outperforms baseline models, particularly in scenarios where additional supervisory signals are not utilized, showcasing its robustness in dynamic scene reconstruction. Additionally, an ablation study is conducted to evaluate the effectiveness of the alternating sampling strategy and the curated training datasets, further validating the model's capabilities.
What limitations or drawbacks does the CAT4D method have, especially regarding the training dataset and the diversity of real-world dynamic scenes it can handle?
The CAT4D method faces significant limitations due to the scarcity of high-quality, diverse real-world dynamic scene datasets for training. The paper highlights that while there is ample data for static scenes, the complexity and expense of capturing synchronized multi-view videos of dynamic scenes restrict the availability of such datasets. Consequently, CAT4D relies on a carefully curated mixture of synthetic 4D data, multi-view images of static scenes, and fixed viewpoint videos, which may not fully capture the variability and realism of dynamic environments. Additionally, the model's training is constrained by the need to filter out videos that do not meet specific criteria, further limiting the diversity of the training data. This reliance on augmented and synthetic data may lead to challenges in generalizing the model's performance to complex real-world scenarios.